In this video, I'm going to be talking about Kolmogorov's axioms. Kolmogorov was a famous Soviet mathematician who in 1933 published a set of 3 axioms that is considered to be the foundation of formal probability theory. In a sense, you can view Kolmogorov's axioms as the bedrock upon which probability theory lies, and almost all important theorems of probability theory can be deduced by starting out at these 3 axioms. But before describing these axioms, I'm going to be introducing a small toy problem that we will use to practice on using these axioms. In this problem, we consider that you have one 6-sided die, but it's not a normal die, because this one has been manufactured such that the outcomes 1, 2, and 3 will turn up twice as often as the other outcomes. Given this premise, we have 2 questions. First, if you roll this die, what is the probability of getting an odd number? And second, what is the probability of getting an even number? Now, this problem is fairly simple, and I think many of you could solve it even without learning about Kolmogorov's axioms. So I would recommend you to pause this video now and solve the problem before coming back. Okay, welcome back. So let's get started with the theory. Now, to begin, Kolmogorov's axioms are based on the idea of describing probabilities using set theory. So let's describe some basic terminology that we'll be using with these sets. One of the most important sets that we will look at is this set omega, which describes what we call the sample space. Now, in any random trial, the sample space is going to be all possible outcomes that could take place from that trial. So for instance, if you're describing the roll of a 6-sided die, then the set omega should contain the 6 possible faces that this die could land on. So this would be the set omega in that scenario. And any element in omega is called an outcome. So for instance, if we're talking once again about a 6-sided die, the outcome 3 would be one element that exists inside of our sample space. And subsets of our sample space are called events. So for instance, we could define an event A to be that we roll 2 or less. Then this would be a subset of our sample space, or more specifically, it would be the subset that contains the outcomes 1 and 2. Okay, so now we know that the sample space is the set that contains all possible outcomes, and that an event is a subset of that sample space. Now we can consider some operations that we can take on these sets. For instance, consider that we have 2 events, A and B. Then we can do something called the union of A and B, and it looks something like this. And what the union means is that we consider all outcomes that exist in either A or B. So let's use the same set A that we had before, which was the outcome 1 or 2 when we roll a 6-sided die. And let's say that B is a set that contains all even rolls with our die. In other words, B would contain 2, 4, and 6. In this case, the union of A and B should contain all outcomes that exist in either of these 2 events. So the union of A and B is going to be the set 1, 2, 4, and 6. Visually, you can see that on the left here, we have a union B. Okay, another common operation that we can do on these sets is the intersection. So the intersection of A and B contains all outcomes that are part of both of the set A and B. So in other words, this would have to be an event where both of the other events are true. And using our previous example, this would be a very small set that only contains the outcome 2. And visually, we have this displayed on the left, right here. So with that basic terminology out of the way, we're now ready to state Kolmogorov's axioms. The basic idea here is that these three axioms should be obvious to you. Because for an axiom, we do not provide any proof. Rather, this is the basis that we simply assume to be true. And then using this basis, we prove the more difficult or unintuitive aspects of probability theory. So hopefully these three axioms will be obvious to you, but let's go over them one by one. So the first axiom states that for any event, the probability always lies between 0 and 1. So let's take an example. If we take the event A that we had before, in other words, that you roll a 1 or a 2 on a fair die, then the probability of that event A is going to be equal to 1 over 3, which is clearly a number that is between 0 and 1. Okay, so 2, here we're saying that the probability of any outcome in the sample space should be equal to 1, or in other words, 100%. This also seems intuitively correct. If the sample space is defined to contain every possible outcome, then the probability of one of those outcomes occurring should be 100%. And finally, this third axiom posits that two events are mutually exclusive. So before we describe the axiom, we have to say what mutually exclusive means. Let me clear this off. So what mutually exclusive means is that two mutually exclusive sets have an intersection which is the null set. Or in other words, the two events have nothing in common. So if we look back at the A and B events that we described before, they were not mutually exclusive events because they both contain the outcome 2. So let's think of a different event. A, we can keep the same. Let's say that this is still the outcome 1 or 2. But perhaps B is now just that you roll 5 or higher. These two are mutually exclusive events because they have no outcome in common. In other words, their intersection is the null set. Okay, so what the axiom then states is that given that this is true, which it is for this case, then the probability that a union of these two events are true is equal to the probability of the individual events summed together. So what are we saying here? Here we're saying, what is the probability of rolling 1, 2, 5, or 6? That probability should obviously be 4 over 6 by the classical definition of probability. And on the right side, we have the probability of A, which should be 2 out of 6 because we have 2 outcomes. The probability of B, 2 out of 6, which is also 2 outcomes. We take the sum, and we see that this equality holds. And this is always going to be the case, given that you have two mutually exclusive events. And that's it. The axioms are really that simple. But this is the foundation upon which all of probability theory is built. Now we will try to solve this problem using Kolmogorov's axiom. To begin, I will define an event that I'm going to call di. And this is the event that only contains a single outcome, namely I. In other words, for example, the event d4 is the event that you roll a 4 on this loaded die. Then the event that we're interested in here is the event that you roll an odd number. And from our set theory terminology, we know that that is equal to d1 unioned with d3 unioned with d5, because these are all the odd numbers that you can roll on this die. And in particular, we're interested in the probability of this event. So we're looking at the probability of this here. Now this looks almost exactly like Kolmogorov's third axiom. It's just been extended to one more term, but it's trivial to show that this will follow the exact same rule as Kolmogorov's axiom. In other words, that we get the sum of all of these three individual events. Now, if this was a fair die, we would be done here, because we would know that the probability of any of these events would be 1/6. But it's not a fair die, so we're not done. We still have to determine what these individual probabilities are. What we do know is that the probability of rolling one of the first three numbers, for instance a 1 or a 3, should be twice the probability of rolling any of the higher numbers, 4, 5, or 6. In other words, we can actually restate this equation here as this should be twice as probable as rolling a 5. So this is 2 times the probability of the event d5. The same goes for this one. So this is also 2 times the probability of d5. And finally, we let this one remain the same. So here we just have the probability of d5. And this we can clearly simplify to just 5 times the probability of d5. Okay, so this is already taking us quite far along the way. Now if we can just figure out what is the likelihood of rolling a 5, we can just multiply that likelihood by 5, and that is the probability of getting an odd number. Okay, so let's remember this, and I will clean the board to make some space here. We can write down this here, just so that we remember it for later. Okay, so the question now is, how are we going to determine this probability? Well, once again here, we can take advantage of Kolmogorov's axioms. So let's now look at the event that we roll anything. In other words, the probability of d1 unioned with d2. And then I'm just gonna make 3 dots here and say that we union all the way up to d6. From the third axiom, we know that this is equal to the sum of going over all 6 individual events and adding up their individual probabilities di. But if you look at the left-hand side here, this is now the union that contains the entire sample space, because this contains all 6 numbers, which is the whole sample space. So this thing on the left here is equal to the probability of omega. And if you look on our thing to the right here, this is the probability of d1 plus the probability of d2 plus the probability of d3, which are all the same, right? The 3 low numbers we know have the same probability. So let's write this as 3 times the probability of any one of the 3 first numbers. Let's pick 1, for instance. And then we have, after that, we also have the probability of 4, 5, and 6. They are also all the same. Here we can also pick any one number, but let's take 5, since that's the one that we have up here as well. Okay. And now by Kolmogorov's second axiom, we know that this left-hand side is just 1, because you're guaranteed to get one outcome in the sample space. And on the right-hand side, we can once again leverage the properties of this loaded die. In particular, that the probability of rolling a 1 is twice as likely as rolling a 5. So this is equal to 6 times the probability of d1. Oh, sorry, d5 plus 3 times the probability of d5. And now we can see that the probability of rolling a 5 is going to be equal to 1 divided by 9. And then we immediately get the answer that the probability of getting an odd number is 5 divided by 9, because of what we remember here from before. Okay, so maybe you were already able to solve that first question in a simpler way. And if you did, I think you might have accidentally used some of Kolmogorov's axioms. The point of illustrating this is that these axioms are meant to be intuitive in some sense, since these are the things that we just accept as true and then base everything else of our derivations on. So view these problems as a way to practice deriving things that are less intuitive by relying heavily on these axioms, because that's going to help you when the problems become more tricky and less prone to be solved by intuition. So to do one more set of practice, let's look at this second question. Now I'm going to define a different set of events here. So I will define the event E as the event that you get an even number. In other words, this set is going to contain all of the even outcomes 2, 4, and 6. And O as the set that you got an odd number, so 1, 3, and 5. Now, the union of these two sets is clearly going to be the entire sample space. So let's write this out. So we have the union of E and O, and the probability of this union by the third axiom of Kolmogorov is going to be the probability of an even number plus the probability of an odd number. And then, as we said, this is the sample space. So by Kolmogorov's second axiom, this has to be 1. So now we can see that the probability of rolling an even number plus the probability of rolling an odd number is going to be equal to 1. And we already know the probability of rolling an odd number. That is what we solved in the previous problem. So we actually have here that 1 is equal to the probability of rolling an even number plus 5 divided by 9. And now it is immediately clear that the probability of rolling an even number is equal to 4 divided by 9. Okay, so to recap, we have gone over Kolmogorov's 3 axioms, and we have applied them to solve 2 different problems. If you're interested in learning more about probability, I can recommend you to use these axioms to prove some famous theorems of probability theory. I've written down 2 examples here that can be proven using only these axioms. So the first one is the complement rule, and the second one is the addition theorem of 2 events. Then, if you're interested in watching more videos, I have made 2 videos previously. I believe this is my 3rd, and I'm planning to make 12 more. Finally, a lot of the material that I get for making these videos is inspired by the book Probability and Statistics, Theory and Applications by Gunnar Blom. So I can definitely recommend reading this book as well.